Section 10.3 is about the thermal expansion of solids and liquids, and I like to talk about um, this in terms of some abbreviations. Thermal coefficient of linear expansion, thermal coefficient of area expansion, and thermal coefficient of volume expansion. So linear, area, and volume is essentially the ideas. Um, the first equation here in this section is about the thermal coefficient of linear expansion, and they call this one alpha, and basically goes delta L equals alpha L sub naught delta T. I'm going to write that as delta L over L equals alpha delta T. So how this works is that if you change the temperature a little bit, then there is a proportional change in the length based on alpha, the thermal coefficient of linear expansion. If you did the same thing with the thermal coefficient of area expansion, it would be delta L over L equals, and it turns out it's 2 alpha delta T. I'm sorry, delta A over A. Delta A over A, and the thermal coefficient of volume expansion, delta V over V, is 3 alpha delta T. Now they've got different letters for the thermal coefficient of area expansion and volume expansion. See here for the area expansion, they use the Greek letter gamma. So, but it also says right there, gamma equals 2 alpha. So you don't technically need to use gamma, you can just use 2 alpha. And then it says in equation 10.6, delta V is equal to beta V sub naught delta T, so they call the thermal coefficient of volume expansion beta, and the thermal coefficient of area expansion gamma. But gamma is equal to 2 alpha, and beta is equal to 3 alpha. Okay, why does it come out to be 1, 2, and 3? Let's have a look at an example. We'll say I've got an area that looks like this, and we've got area equals L squared, right? And then we will have this side increased by delta L on this side and L on this side, and this side increases by delta L by L. So the new area is equal to L squared plus 2L delta L. And we'll just ignore this little part right here, which would actually be delta L squared if you did work it out, but it's so small, we'll just ignore it. Okay, let's look at what is delta A over A. Delta A is this part that changed, 2L delta L, and the original A is L squared. So dividing that out, it's L over L squared is 2 delta L over L. And delta L over L was 2 alpha delta T. Whoops, 2 alpha delta, and I want the capital T for temperature. Okay, so you see it's 2, essentially. Okay, let's do the same thing with a cube. And the volume of this cube is L cubed. And then we will add a little segment on this side, which has volume equals L squared delta L, a little bit to this side, which is L squared delta L, and a little bit to maybe the front side, that is L squared delta L. So that is plus 3L squared delta L. Again, I'm leaving off a bunch of things here. Some of these sections here, 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 which would be plus 3L delta L squared, those three rectangles, and then this one of those will be left with one tiny little section there, which will be delta L cubed. But those we can say are small enough that we can just kind of ignore them. So our delta V then is just this part here, 3L squared delta V, delta L, divided by our original volume is L cubed. And once again, we find we get 3 delta L over L. So the change in volume, and delta L over L was alpha delta T. So you can see that it is 1, 2, and 3. Now you can, if you wish, remember that they call this one alpha and this one gamma and this one beta. I think they mix those up kind of weirdly. I generally refer to them as the TCOLE, the TCOAE, and the TCOVE, the thermal coefficient of linear area and volume expansion. So this is not the first time we've seen a delta L over L. Here we have delta L over L equals the thermal coefficient of linear expansion times the change in temperature. So a little change in temperature will cause the object to stretch. Usually as you heat it, it gets longer. As you cool it, it gets shorter. We've also seen another equation where we say force over area equals Young's modulus times delta L over L. This was if you actually apply a force at the end of the object, then it will shrink or expand or stretch depending on whether you put a tension force or a compression force on it. Combining these two equations is the subject of example 10.3, expansion of a railroad track. So let's look at that. A steel railroad track has a length of 30.000 meters, and the reason they're giving so many significant digits there is because we're going to see an expansion that's in the terms of millimeters or something like that. When the temperature is 0 degrees Celsius, what is the length on a hot day when the temperature is 40 degrees Celsius? Okay, so first let's find out what is delta L over L equals to, oh, we need another given. We need to look at the table 10.1. For steel, alpha is 11 times 10 to the negative sixth. And I think, oh yeah, it's per degree Celsius. 11 times 10 to the negative sixth per degree Celsius. I'm also going to cheat a little bit here and write down Young's modulus. I didn't look it up in the back, rather I went down here and checked out where it says Y, and it says 2.0 times 10 to the 11th pascals. But there was a table of Young's moduluses for steel that included steel. I think it was table 9.2 in chapter 9. All right, but anyway, for the answer to part A, we need alpha delta T for this, and more specifically, okay, well, let's find the delta L first, which is 11 times 10 to the negative sixth per degree Celsius times 40 minus 0 degrees Celsius. So that gives us the fractional change in the length. It's 4.4 times 10 to the negative fourth part. Would actually be 0.044%. But now we want the actual change, delta L, which is going to be equal to L times alpha delta, well, you know what? I'm just going to write delta L over L, which we already solved. So L is 30 meters, and then our delta L over L is 4.4 times 10 to the negative fourth, which comes out to be 0.0132 meters. That is 13.2 millimeters. And so our final length will be the 30 plus the 0.0132, or 0.013, since the original just had 3 sig figs, or 3 decimals. This should just have 3 decimals. So the track lengthened by 1.3 centimeters. Part B asks, suppose the track is nailed down so that it can't expand. What stress results in the track due to the temperature change? So what I'm going to do now is figure out the stress, which is this value here, equals Young's modulus, 2 times 10 to the 11th, times our delta L over L, which was 4.4 times 10 to the negative fourth. So this was the strain caused by the temperature change. This is the stress, and this is Young's modulus. And this comes out to be 88 million newtons per meter squared. 88 million pascals. Significant amount of stress. 101. I guess I was just curious, and it comes out to be about 870 times atmospheric pressure. Remarks: repeated heating and cooling is an important part of the weathering process that gradually wears things out, weakening structures over time. Question: what happens to the tension of wires in a piano when the temperature decreases? Well, my first thought is that the piano wire should contract, and therefore the tension would increase. But then it occurs to me that the other parts of the piano have either may be made of wood or some other substance, which also may contract and have either a greater or smaller thermal coefficient of linear expansion. And it may depend greatly on the difference between those two things. So exercise 10.3, what is the length of the same railroad track on a cold winter day when the temperature is 0 degrees Fahrenheit? So for the first thing on that one, we want to convert Fahrenheit minus 32 equals 1.8 C, or is it C over 1.8? Man, I was going to memorize this. Okay, I checked. It's right. Okay, so minus 32 over 1.8 is equal to our Celsius degree. So our temperature will be negative 17.8 degrees Celsius. So let's find our proportional change. Delta L over L is equal to alpha, 11 times 10 to the negative 6th, per degree Celsius times delta T, which I'm just going to not worry about which one comes first, 17.8 degrees. And let's go ahead and multiply that by 30 meters. It turns out that the delta L, since it's colder, it will be shorter by about 5.8 millimeters. And when you subtract that from 30 meters, you get 29.994 meters.